Okay, let's go ahead and break into our explore number 3 of the history of life on Earth. Make sure you put your date, make sure you label it. This will be from Living Earth 3.1.3. The essential question: what is an evolutionary tree diagram? Okay, so go ahead and put that down, your essential question, and then tell me what you know. Tell me what you think. Okay, hopefully you took a moment to write down some thoughts on what an evolutionary tree diagram might be. An evolutionary tree is basically a diagram, an illustration that models relationships between different organisms. It models their similarities, it models their differences, it kind of shows where common ancestry exists. That's kind of it in a nutshell. Um, So, if we take a look at letter A, all existing organisms have evolved from other organisms, and all have come from a common ancestor. You may take a look at ourselves, the eukaryotes, for example. You might look at plants, you might look at bacteria and fungi and protists, all these different types of life, these different domains and kingdoms, and yet they're all related. They all can be traced back to a common ancestor. Evidence that we have for that, number one, would be things like more recently DNA similarities. We're able to take a look at the DNA of different organisms and take a look, trace back different species to their common ancestors, and we can see where mutations have occurred. And we can even map approximately when those mutations happened, when a species may have diverged. That gets into molecular clocks and the background rate for mutations. The fossil record also gives us a little bit of, not just a little bit, it gives us plenty of evidence that allows us to make some inferences as far as relatedness goes, as well as chronology as far as timing is concerned. Letter B, evolutionary trees provide us with a model of these relationships, much like a tree branch which attaches to a tree trunk. At the trunk, you may have the most basic original common ancestor, and as you move up the trunk, you start to have forks. Each fork is going to represent some kind of speciation, and sometimes a whole branch, even with all of its smaller branches, may represent like a kingdom or a phylum. When you get down to the branch tips, these are going to be getting down to your individual species. Okay, your common ancestors would be at the nodal points, the bases, where these branches actually attach to the main branch or a bigger branch. The forks are splitting off, right? And when you get to branches that just stop, those are going to usually indicate extinction, where those organisms no longer are with us. There's a term that we use in biology. We call it phylogenetics, and hence what we've been calling an evolutionary tree can actually be called a phylogenetic tree. Phylogenetics is the study of evolutionary relationships. So this tree just looks a little bit different than an artistic living evolutionary tree, but in essence, it provides us with similar information. We have our little stems. This is where we identify the specific species. Where they bifurcate, where they split, those are your nodes. And that should not say notes, that should say node, Nodes. Okay, so that just looks like it's a little messy there. Maybe I should just go ahead and correct that right now, just in case you are not listening to this. There's always that chance, right? So let's just take that. Let's just make sure that looks a little cleaner, okay? Node. Okay, that's a node. And that represents a common ancestor. when you have a number of different species that can be traced back to a common ancestor, then we call that taxonomic unit a clade. Okay, I don't have the word taxonomy here, but taxonomy, as you'll see later on down in here, taxonomists, these are people who use phylogenetic trees to represent classification of organisms. They break the phylogenetic tree into taxonomic units. And this unit here would be called a clade. Okay, and includes all the organisms with a common ancestor. So this whole big thing here could be a clade, just depending on how what you want to what you're referencing. Okay. Okay, so and time is represented. So more present time is further out on the branches, and depending on how far you are here versus here, this gives you a sense of time. This represents an older period of time stretch, and this represents that older time plus more recent stuff. So these guys would be more recent developments. There's another term we use called cladograms. Again, that should make sense because these things are called clades. So when you're taking a look at a branch in particular, perhaps, maybe not, you can make this a big clade. You're trying to show what unique synapomorphy, it's not a term in your text, but what unique trait distinguishes all the animals coming after that point. So in this case here, the synapomorphy between A and B, all the animals after A, so from B, C, D, E, and F, they're going to have this new trait. A does not have that trait. Okay, and so the differences between all these different lines is going to be marked by synapomorphies. And your common ancestors, again, are going to be at the nodes, and your species are going to be represented at the tips. So anyway, boy, that's all there is really to this. Okay, so we're just kind of, since we're talking about the history of life on Earth, we've explored the geologic time scale, how Earth was formed, how life kind of generally formed. We've talked about life branching out, speciation. We've talked about life ending, extinctions, and now we're kind of just talking about evolutionary trees, a concept of evolution coming from Charles Darwin, and how we can map the development of all the different species on Earth. So I hope that was helpful, and we'll talk to you soon.